yes. Okay, click OK if you will probably be asked to do that. Okay, so now if you think that this is your vector field, then this is definitely a special point. And at this point, where the arrows are all pointing into one local point, it displays the divergence is negative. Okay, showing that the like water or whatever is leaving the scene, right? So the leaving like getting away from the field, right? So and this is, you can think of it as a sink, and in sink the divergence is negative, and you can think alternatively as about a source, right? As I have shown to you here, the example of the spring, where spring is stemming from underground, right? And then and the if your field is, for example, the vectors of elementary volumes of water, right? Then you will have some outgoing, set of arrows of the field, and in this place the divergence will be positive, telling you that there is a source of your vector field in this point, okay, in this location, okay. So, and this was I showed to you some arguments why this or that differential operator actually describes this, like in this case describe the sink or source by considering a small volume, and then trying to say that, for example, in this volume, if there are no sources or no sinks inside, the amount of water that flows in has to be equal to the amount of water that flows out, right? And we just simply compared these two quantities, subtracted, and then we found this quantity that is basically measuring the amount of new stuff that appeared inside this elementary volume, okay? And that's a divergence, okay? So, and this is kind of natural, right? Because you simply look how your X, Y, and Z components change along each along the corresponding axis, and then you just sum these two, okay? So then we looked at the curl. This is another characteristic which tells you about the uh, the extent to which you have rotation in your field, right? The example of this, again, if we talk about water and the vector field, is you can think of those like of this as a set of vectors attached to elementary particles of water, let's say in the toilet tub, right? And when you flush it, you see this rotation, and that's the point. In this point in the center, you have high rotor, high curl, and it's very similar to measuring the uh, how you call it, the angular speed, right? So that you can, when you measure the angular speed, you usually talk about rotation within some plane, and so your angular speed, in fact, is a vector, and the length of this vector is equal to the to the speed of rotation, to the number of turns per, let's say, second, and the orientation is simply perpendicular to the plane in which this rotation is happening, very similar to the curl. And the curl is defined by this incomprehensible, maybe thin, but in fact these are just the differences along each of the directions, like in this loop, because we looked at the circulation, right? And we wanted to see if there is non-zero circulation, if there is non-zero similarity, again, right? Because this is basically again, you can this basically also what we are doing here, it's a scalar product in some sense. It's a vector product, but the length of the of this basically the size of the curl, if you rotate things properly, I'm not going to describe it here, but it will again be measuring, in fact, similarity between the vector field pattern and this pattern of rotation that we are interested in, okay? And that's all, right? And then we simply looked at the differential expression, and this is something that when applied to the vector field can tell us about the amount of rotation that is taking place in the vector field, okay? So um and with this, so that you now know what your divergence is and when your rotor is, we started to look at Maxwell equations, and Maxwell equations tell you that the divergence of electric field, right, is your electric field lines, the divergence of this electric field is basically equal to the density of charges, which we look, right? This is reasonable, right? You can think of a single charge, positive charge, and you have arrows pointing outward, right? So that's a source of electric field. And then you all know that, from school, this is how you call it, the rule of a corkscrew or whatever, I forgot how it's called. Basically, if there is a current floating in a certain direction, then the magnetic field is is taking place in the plane perpendicular to the current direction, and forms circles, right? So that's why the rotor of the well, sorry, let me first go to this question. The rotor of the magnetic field is basically proportional to the strength of the current, right? And then there is also this component, but we will not use it. So I'm not talking about this now, not to confuse you even more. So basically, it tells you that the vector of the current density can be treated as a rotor of the magnetic field, right? It's basically the rotor is something which is pointing in the plane perpendicular to where the magnetic field is happening, right? And the magnetic field, the stronger the J is, the larger the J is, the stronger the magnetic field is. So everything is quite reasonable, right? And then the same story, but about the electric field, that basically change in magnetic field produces electric field, the rotor of the electric field. Okay, so the change in magnetic field along some direction produces magnetic field, sorry, produces electric field in the opposite direction in terms of magnetic, sorry, change in the magnetic field causes electric field in the orthogonal plane. This is why you have a rotor here. In this orthogonal plane, these electric field lines are rotating, okay, and they are pointed at the direction opposite to the field change, meaning that kind of designed to compensate this field change. When the field disappears, the electric field comes and wants to restore the disappearing magnetic field. And the same and very similar story with this magnetic field, right? So, but then we looked at the quasi-static approximation. We said that the changes of electric field and magnetic field in the brain, given the conductivities and given the frequency range of the brain sources, are slow, and therefore we arrive to we can talk about quasi-static approximations. And I refer you to the literature, to the book, and to the Matti Hamalainen's paper, and to the book by Risto Moniemi and Yuka Sarvas, where they show why this quasi-static approximation works. Okay, and this quasi-static approximation, since are even simpler, all we have is that the divergence of electric field is simply the density of your charges, and rotor of E is zero, meaning that this vector is this vector field is curl free, and the rotor of B is simply the current. Okay, so the current floating is the simple Ampere's rule basically, but in the differential form, right? So the current produces magnetic field. Yeah, that's it. Okay, so and then what's important here is that this curl of the electric field is zero. Okay, that means that I'll skip this. It means that the electric field, uh, you can think of this very much as you think about the Earth's gravitational field, okay, which you all used to, right, from childhood, from school days. You were able to, in the physics classes, right, the first thing you learned, well, no, I know the first of all, the second, in the second year when you study physics, when you start talking about forces, you learn the gravitational force, right? And your gravitational force is m times g. Okay, so here g is equivalent to E. Okay, so G, the size of G, right? The magnitude of G is equivalent to the magnitude of E. The direction of G, it's always towards ground, right? So now these vectors are, you can think of them, they are equal to the free fall acceleration, and the further away from the ground, of course, the smaller this value is, right? Uh, and then and that's your G, okay? M is your charge. Here it's an electric charge. Here M is a mass. Gravitational field acts on a mass, okay? Electric field acts on a charge. In order to compute the force with which electric field acts on a charge, you have got to multiply the charge by the force, right? By the strength of the field, right? By the strength of the electric field. So you multiply E times Q, you get Coulomb's force, right? Okay. So here you multiply the mass, which is equivalent to charge in the electric case, right? You multiply M by the strength of the field, by G you get Newtonian force, right? You get gravitational force, right? Okay. Um, why I started talking about the curl-free thing? Okay, this curl-free thing basically says that there are no such things in your field. Okay, which is good in your electric field, not magnetic, but electric field. Okay, uh, and this means that you can take the work A, okay, the physical notion of work, the labor, right? The work, yes. The work is does not depend on the how the contour is organized. You know, the work of moving a body of mass m around this contour. It doesn't, or from this point, for instance, to this point, right, or from zero's point, from the zero level to level h, it does not depend on the path how I'm moving it. You know, you can move it this way, you can move it this way, you can move it directly. The amount of fuel, let's put it this way, you spend uh, to propel your vehicle that is moving this mass, okay, or and including the mass of the vehicle. It doesn't depend on the trajectory, but it depends only on the difference between the levels, okay. And these levels are in gravitational field, we in electric field we call we encode these levels with so-called potential function, okay. And you've heard this word potential in the context of physics because you have all heard about potential energy, right? The potential energy is basically equal in the magnetic field, in the sorry, in gravitational field, it's equal to mgh, okay. So, and but this is energy, but the potential itself, okay, is equal to gh. If you talk about gravitational field, right, it's equal to gh, so it's equal to the field strength multiplied by some distance, okay, by some, right. And the potential difference tells us about encodes basically the amount of work that needs to be done in order to displace a body from one point to another point. And of course, the amount of work depends on the mass of this body. The same as here, if you define some potential function, okay, this potential function, when you divide this potential function by the distance, you get the field you field the strength of the field, right? And when you multiply this potential function, the difference of potentials, by the charge that you want to move, by the amount of charge, by the amount of coulombs, right, which represent the charge, right, you get the energy that needs to be spent in order to move this charge in the electric field. Okay, and this nabla v is nothing but computing the difference delta v divided by delta x and delta v divided by delta y. Then and all delta v's are considered in the first element. They're considered with respect to x, then delta v in the along the y direction divided by delta y, right? And again delta v along z direction divided by delta z, right? So it's basically the difference of the potential divided by the difference in the distance. And of course, because it's a differential operator, then you say that the delta z, delta x, delta y go to zero, okay? But so again, you understand, right? So this is the potential, right? And the gradient of the potential is when you take the potential and see how fast the potential changes as you move in space, okay? And that's very reasonable to say that if this changes fast, then the field is very strong, right? Because right, because the field lines are working actively, and the strength of the field is very different between the 2 points, which is reflected in the difference of the potentials, right? uh that's all. That's kind of intuition behind this whole thing. Okay. uh is it clear? I mean, any questions, please? Then say it's clear.
Can you give like some examples, which one is faster, like the comparison of some fields, real
Well,
life
okay. Well, I can tell you. Okay, if you refer to the gravitational field. Okay, first. Okay, so if you consider gravitational field right on the Earth's surface, right, like where we live, like in biosphere, right, in this location, and you consider the gravitational field of Earth, I don't know, like uh, 10,000 or like 20,000 kilometers above Earth. Okay, so the gravitational field 20,000 kilometers above Earth is weaker than the gravitational field right on the surface of the Earth, right? This is, or if you consider gravitational field of the Earth and the gravitational field of the Moon, okay? On the Moon, in order to move a body in a certain direction, in a certain amount of like meters away from the surface, you will have to spend less energy than you have to do if you do the same as compared to the case when you do it around the Earth's surface, okay? And this work is basically the difference between the two potential energies, the potential energy on the surface and potential energy on the height, right? And this potential energy is proportional to the potential difference, okay, to the difference of potentials, because on the Earth's surface, you have gravitational field potential 0, and at like height of 1 meter, for instance, you have gravitational force potential equal to gh, which is g is 9.8 meters per second squared multiplied by meters, right? So it will be meters squared divided by second squared units. Okay, so very similar thing in the electric field. You can think of, like, say, electric field which is created by a single charge, and electric field created by two charges. Okay. Well, if you take a single charge, and you have another charge, which is, let's say, another positive charge, right? And you want to move your positive charge close to this first positive charge, right? Then apparently you know that the two charges will be trying to detract from each other, to get detracted from each other, right? So that when you move, you will have to apply to do some work in order to move this, because you will be going against the field lines, right? The same as here, you in the gravitational thing, you will be going upward against field lines, and when you're going downward, you are going along the field lines, and the field is helping you, right? So if you have a positive charge and you move another positive charge to it, you will have to spend certain energy, which is proportional to the potential difference. And now this is electric field potential difference between the point where you started moving and the point where you finished your move, the movement. Okay. Then if you take two charges, then you will have to spend twice as much energy, right? Because the force will be stronger, because you will now be the field will be acting on these two positive charges, will be acting twice as strongly as compared to when you had only a single charge. Okay. But in this case, the potential difference is the same, but the field the charge is twice the charge, and so the energy is the charge multiplied by the potential difference, and therefore it will be twice as large. Okay. And this potential, you may think that you never encountered. No, this potential is you very much aware of. The difference of potential is the voltage, between two contacts. Like if you take a battery and you take one contact, you take another contact, you have potential difference between electrical potential difference between these two contacts. Okay. And it is this potential difference which allows a lamp, for instance, to shine when you connect the contacts to the lamp, because it creates a current, and current floating through the let's say, through some spiral, right? And the spiral gets heats up, and you get the light. Okay. So the potential difference is something that allows you to do the work, which describes the amount of work that field can do. Okay. And the reason I stopped on this is because potential is kind of important in deriving the equations, in solving the Maxwell equations and deriving the forward models that we'll be talking today about. Okay. But it's I think it's an important concept. That's why I stopped on this. Okay. So that to show you, for example, also that sigma times gradient of v. The gradient of v, you can think of this as as basically the minus gradient of v is your field strength, right? And then if you multiply it by the conductivity, by the extent to which the substance is conductive, right? This is basically your current density, which is in fact your Ohm's law, right? The Ohm's law, which states that the current is equal to the voltage divided by the resistance, right? Here, if you go into the elementary volume, then you get the gradient of voltage, or gradient of voltage, which is your field strength E, divided by the conductivity per small element, per small volume of your substance, of your media that you are working with. Okay, so and it this secondary currents, so these guys create secondary currents. Like if you create different, if different points in your medium uh have different potential, then of course there will be current floating if the conductivity is non-zero, right? There will be current floating between these 2 points, trying to equalize the potential, right? Trying to make so that the potentials are identical in these 2 points. The same with the battery, right? If you have two contacts which are not connected, then the battery keeps its charge, right? But as long as you connect it, the current starts floating, because the goal of the current, the goal of this process is to equalize the potentials of the plus contact and minus contact of your battery. Okay, so you can think of these 2 points as two locations where the potential is not the potentials are not equal, and as soon as you place this in a conductive medium, the battery starts discharging, the current starts floating, and the potential difference starts decreasing. Okay, if you could, okay. um All right. So uh, then we looked at the Laplace equation for the potential. Basically, what it tells you. Okay, if you look at the volume in your, let's say maybe in the brain or whatever, where there are no where there are no um, where there are no currents, okay, and then if you take the if you take these two equations, if you look at the second equation, second Maxwell equation, which tells you that, or the third, whatever, or the fourth, yes, actually the fourth equation, which tells you that the rotor of B is proportional to the current, and then you take the fact that the current is, we will look at this like in more concrete details, but it's equal to the primary current, to those currents that float in dendrites, right? But which Marsha told you about and I mentioned, right? And the other currents, which are volumetric currents, right, which are created by this primary current, right? Because you have to always in the conductive medium, you always have the currents that are closing the loop, right? Like with this battery, right? So then the total current is equal to this guy. And then if you solve this whole thing, okay, you will arrive to an interesting equation, which tells you that so-called Laplacian of the potential, it's nabla squared, the Laplacian of the potential, Laplacian of the potential is equal to the current density, basically to the divergence of the current, okay, to the divergence of the current density. Okay, okay, that might not be very intuitive, but let me try to somehow explain this. Okay, in most of the play, okay, and this is, of course, we don't put R and T, because we usually talk about these kind of things happening in a certain location and space and a certain moment of time, right? So this, of course, is changing over time, is changing over space, right? So that tells you in certain location in the space where there are no primary currents, the Laplacian of V of potential is zero. Okay, this is just a constraint that is put on the Laplacian. Okay, so that, okay, for instance, you have current floating in some place, right? Okay, then Laplacian has to, then the current defines this Laplacian, okay, this value of this Laplacian. I'll tell you what it is just in on the second slide. Okay, but if there are no current floating, then the Laplacian has to be zero. Okay, what does this mean? Laplacian equal to zero. Okay, look, This is the Laplace equation, okay? This is basically just a different way of writing this, because nabla is your differential operator. Remember, d dx, d dy, d dz, right? And then when you raise it to the square, you get the second derivative instead of the third derivative, or instead of the first derivative. And I'm looking at only on the plane for simplicity, okay, only in 2 dimensions. So it's basically equal to the second derivative of u with respect to the distance when you, as you move along x, and the second derivative of the potential when you move along y. The sum of these guys is equal to 0. It's very difficult. From this, it's impossible to understand what this means. Absolutely impossible. It's absolutely impossible to make any feel of this, okay? But let me tell you this. Remember, when we were talking about differential operators, we were always starting from the definition of the derivative, which is the limit of the ratio of the function change and the distance change, right? Or the argument change, right? In this case, our function is a potential, and the distance is a physical, and the argument is a physical distance, right? So, okay, let's consider this equation on a grid, and let's assume that this grid is small enough. Okay, it's fine enough. It has relatively small distances between nodes, and this is just simply our plane x and y, and we just define a set of nodes here. Okay, right? So you can approximate this derivative, right? This the second derivative using simple differential finite difference scheme, right? So like the first derivative of u with respect to x is equal of u at location x plus h, okay, and at some y, minus u at x and at some y, right? So basically, we increase the distance a little bit and said, okay, what is the potential there? Okay, and how it relates to the potential at the central point, which is xy, right? And we divide it by h, right? This is one way of approximate this. Another way, you can say that you can go not forward, but you can go backward with the second guy. It doesn't matter actually. Plus minus is the same. So um, and then if you then if you then and this is another way of approximating it. You can go from the central point, you can go to the left by h and to the right by h, and then you divide already by 2h, okay, which this pretty much the same schemes, then slightly different numerical properties they have, but you know. So then the second derivative is the first derivative of the first derivative, right? So now you have to take du dx, and now this is your function, and you have to use exactly the same rule and substitute already this guy into this rule again. You understand, right? You have just to take the second derivative, right? And then it's u has to be here, of course, u of x minus h. This is your second derivative, okay? This is the second derivative of u with respect to x, okay? So it's basically 2 points here and here added together, this one and this one, for instance, right? This location at this point and at this point, and minus 2 values at the central points, right? You can write it in a problem simpler, and you remember that second derivative is equal to 0, right? And you can do the same for x, and you can do the same for y. And then if you define the values of u at x and y as uij, right? Uij. And then if you define values of x minus h as I minus 1, because just a step, one step is size h. So, and then those are the values of your field on this grid. If I tell you that this guy is equal to 0, then it means that this equation has to hold, okay, or this equation has to hold, okay. If you just group the guys, take uij on the one side and the neighbors of this uij, for instance, here to the other side, you can see that the value of the field at this point is of the potential. Sorry, in this case you have a potential. The value of the potential at the central point is equal to the sum of potentials with negative sign, right? To the sum of potentials in the neighboring points. Okay, so it imposes some limits onto how your potential function can look. Okay, this is like, for instance, okay, if I tell you that the body is moving with the speed v, and I draw you a grid like of 1 second, 2 seconds, 3 seconds, 4 seconds, and etc., right? Then you know that the the trajectory of this body has to go with, with respect to the axis t. Uh, it has to go with some angle, right, which is proportional to the speed, right? And of course, this line can move and can move upwards, can move downwards, because it depends. It depends on which distance you started, how you count where is zero, right? But if you move it, it doesn't matter. The shape of of the curve still remains. It will still be it still be a it will be a line, and the angle of this line with respect to t-axis will be equal to to the velocity. It will be equal to the speed, right? That's a constraint that is imposed by the differential equation. It means that the displacement at time t plus 1 minus displacement at time t divided by by 1, basically, right? In this case, is equal to your speed. Very similar here, but in 2 dimensions and about second derivatives. Okay, it's an equation that imposes the constraints onto how the potential can change. Okay, how the potential can look. Okay, and then you basically, in order to, one of our goals will be to find this potential distribution. And you usually approach this by saying that, okay, I know what the potential values are on the boundaries. Okay, let's say if we talk about our tasks, and we say that in the infinity, for instance, our potential will be 0, right? Okay, that's one. Well, this is one thing. And another thing, we use we go to the more compact equation like this, then we can say that at some locations we may have primary currents. Some locations in our grid we might have primary currents, and then our equation will be almost the same, except that we have this constant that is changing this relation, right? So basically we will have not equal to 0, but will be equal to the strength, if you will, of our current source. Okay, and then you simply create a set of equations for each of the potential values on your grid and to solve it. Okay, I'll just bear a little bit. Okay, okay. So that's the thing. That's sort of uh, like like I don't know, some necessary introductory thing which you probably found very frustrating. And I promise you we will not come back to it. Okay, very much. Which is maybe during the test will be some simple problem, very simple problem which simply guides you through some steps, and you will find something new for yourself. Okay, but let's see what these equations in the long run give you. Okay, so these equations about the whole set of Maxwell equations, right? If you then try and solve them, it gives you the can you by the way, can do you see the, let me try to take a look here, just a second, take a look here, just a second, just a second. uh yeah, yeah, okay, so basically it gives you it gives you the, why I'm not seeing my screen here. Oh, okay, well, whatever. So can you see my screen? Do you see this thing which is floating from the top and covering the formula, or you don't see it?
Yeah, we can see your screen and your mouse moving. Yes.
And you see that b of r is equal to this something incomprehensible, right?
Yes. Yes.
Okay, okay, yeah, okay, cool. Because I have this stupid, thing which is control thing, which is always appearing. Maybe hide names, hide stop, whatever. Right, okay. So anyway, so yeah. So now, uh, okay, when we have our head volume, right? And now we take our head volume and we split it into this grid, right? And in this grid, if we want, and with this grid, and if we want to approximate the behavior of the electromagnetic field in the head, in the brain volume, and on the surface, if we want to approximate it using the uh, using these Maxwell equations, for instance, and not approximate, but compute it using Maxwell equations, but compute these equations based on, solve these equations numerically based on discretization of the volume, right? Then we would have to do what I have just described to you here. Okay, this set of equations and etc. This is a complicated stuff, and probably a separate class would be needed for that. But the reason I described it to you, because I just wanted you to get some, maybe at least some very slight feel about what these equations are all about. Okay, why they're actually needed. Okay, so But yeah, so when we will do something much simpler during this class, okay, and then we will refer to so-called integral equations, basically the results of integrating these Maxwell equations within some known, how to say, mm, like media, right? Within some known volumes, right? For instance, you can basically, by solving these equations, you can arrive to this kind of formula, which I'll try to explain to you, okay? So it tells you that the magnetic field at location R, okay, which is due to the currents that are floating in the media, okay, this magnetic field is basically a summation of 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 these kind of guys, okay, which is a vector product between the elementary currents at location R prime and this guy, which in fact measures the direction towards the point when you are measuring your field, right, which is R, which is here, right, here, and where the elementary current source is, right? And so you have to go through all elements in your volume, and you take each little current element, and you plug into this little formula, and you sum all this up. And if your increments are very small, then your summation turns into the integral, okay? And then you integrate it over like elementary volumes, as I already mentioned, and each volume basically generates your magnetic field that is proportional to the current in this volume, um, reciprocally proportional to the square distance, which is r minus r prime, right? This guy here, but r minus r prime in the top and r minus r prime on the bottom to the square, right? To the cube, right? It gives you the square, right? So it's reciprocally proportional to the square of the distance, and this field is pointing in the direction orthogonal to the plane formed by the direction where the current elementary current is floating, and this difference vector, which tells you the relative location of the source with respect to the point where you are measuring the field. Okay, all right. So and this is basically, if you drop this, if you drop the integral, and if you drop this dv, then this is nothing than the school year formula when you had the strength of the current multiplied by the divided by the distance and multiplied by the sine of the angle between the current direction and the point where you are measuring the field, right? Because this is the vector product or cross product between the two guys, meaning that there is so cross product allows you to say that the direction of the magnetic field that is perpendicular to this plane. If you consider, for instance, if you consider this picture as a plane, okay, then your and let's assume that your current is floating in this direction, okay, vertically, right? In some location, right? It's floating in this direction vertically, right? Then this is the distance to, and you are interested in this point, okay, in measuring what the field is at this point. Then this plane created by r minus r prime vector and the current direction, right, which is vertical here, for instance, this plane is of your screen, right? This is a plane of the screen. It means that the magnetic field will be directed through the screen, right? Like let me tell you. Yeah, if the current flow in there, then it will be away from you behind the screen, okay? It will be directed there. So it probably, if I were to draw it properly, it would be a circle here and the cross, which tells you that you are looking into the bottom into the back, into the rear of the vector, okay, of the magnetic field vector, okay. And this is from elementary source, right? And then you have to just go across all such sources, all such vectors of elementary currents, and sum them up, okay. That's probably much simpler than talking about these potentials and stuff, but I just wanted to somehow tell you about those, okay. Sorry, I probably next time I will just not talk about this at all. I will start from this integral equation and refer to school years. But anyway, so look, but there is a difficulty here. The difficulty is the following. This is JR, and this is the integration over entire set where the currents of the entire volume where the currents are floating. Okay, and these currents, as I already mentioned, they can be mm, they can be they can be both primary. They come from the primary currents, right, which comes from our dipole, right, from our dendrites, right. We will talk about dipole later, a little later, and so-called volumetric currents, which are created by the fact that there is electric field caused by charge displacement of charges, remember, uh, and then and then multiplied by the amount of conductivity of the tissue, right? If there is a field strength and there is a conductivity of the tissue, then there will be current, right? And those are secondary currents, okay? And you have to take into account in this formula both primary current and secondary currents, okay? Now, when we set the task of solving the forward problem, meaning that for each source in the brain, we want to see in a set of locations where our sensors are, we want to find the magnetic field and electric potential in these points, right? If you talk magnetic field, of course, will be sensors which are in the vicinity of the head, and if you talk about electrical potential, it will be, of course, the sensors that are attached to the contacts that are attached to the skin, right? Okay, but you want them due to this primary current, and you know this primary current, you know where it's located, you know its orientation, you know everything, right? But you do not know the secondary currents, okay? This is very difficult to know them, basically impossible to know them. And this is where you can either use, as I already mentioned, numerical integration, because you know the rules according to which these currents will behave. And you know the boundary conditions, and you can impose these rules and try to infer these currents, right? Uh, One way. Another way, you can say that, well, okay, what if I am just simply, let's consider, just assume that there is no brain, okay? There is some infinitely sized media with conductivity properties the same as the brain has, okay? Let's just assume this for simplicity, okay? So this way. So this is a picture, right? So you have your primary currents volume here, you have your secondary currents floating, right? And there are many of them, of course, in this whole media. And this media, the whole plane here has the same conductivity, okay? Again, you are interested in the field vector of dislocation, and but that's it basically, right? So now, in this case, there is a very good news that the magnetic field at location R minus, at location R, due to the current source located at point R, this point is R, okay, this is vector R, okay, located here, does not depend on the secondary currents. This is amazing. I'll tell you why. The amazing thing is because that means that you can only limit yourself, you can limit this integration to only the small volume where you believe your currents are. And if as I show you in the next couple of slides, you can replace this integration by just the concept of the current dipole, and that will be just simple multiplication, and then you compute this whole thing numerically, not numerically, just analytically. There's no problem at all. Okay, so again, see the difference between this expression and this expression is that from the integral over the entire volume, we have integral only around the volume G, where the primary currents are taking place, and we are not taking into account secondary currents. Why? Well, because in the infinite homogeneous media, the secondary currents create magnetic fields, but these magnetic fields are such that they cancel each other. Okay, that's fantastic. That's amazing. But this is true. Okay, so if you, for instance, were to compute the magnetic field due to a current to feel to piece of wire, for instance, right, in some non-conductive or media which with a constant conductivity, then you can simply use this formula, and as I show you, you can even replace this integration by just simple multiplication. I'll show you. Okay, so is this clear? The difference between this guy and this guy is clear? And this guy, is it clear? Okay, then ask questions. please. I will take a look at my. I have some problems with connecting this pad. Oh, okay. Okay. Then let's consider. If you don't have questions, then let us continue. Uh, okay. So yeah, I hope it will work. All right. So uh, now assume one other thing. So basically that's what it means, right? That I made them yellow so that you don't have to take them into account. Okay, but still the integral remains here, right? Because there is some integration over some small volume, or maybe not so small, doesn't matter, where you believe the primary currents are floating. But what if you want to model your primary currents by just very simple small current element, right? There will be some current floating along some delta delta, some distance in space, right? So then you can
Excuse me, can I ask a
yeah,
question?
yeah, go ahead,
So
please.
again, about this difference between integration over the entire volume and
Yeah,
in infinite homogeneous media. So we're changing the area of integration. So in the second case, we have G, but in the first place, what we integrating over? For example, our volume form dV prime, it's identical in both cases, above and below. It's the same.
well, no. See, in the first integral, okay, here on the top, right? We
Yeah.
have to integrate over the entire place where the currents are floating, over the entire head volume, basically, in our case, okay? So
Okay.
our integration is taken, from, you can put the borders, you can define like you can approximate the head, for instance, with a sphere and somehow define this integration, or you make this fully numerical thing and you integrate, right? So the integration over the entire volume where the currents are floating, okay?
Okay.
So but if you consider infinite homogeneous media, then then you when you do this integration, nevertheless, okay, you do this integration in the infinite homogeneous media, you go from to infinity, basically, okay, you integrate it to infinity,
But
you
what
solve
is
this.
infinite homogeneous media? What is
Well, like you take a bus of a huge like ocean, for instance, or well, I mean, when you talk about infinite, it means infinite with respect to the object that you are studying. Okay, so if you have current dipole of the size of a I don't know, of a pencil tip, right? Then
and
then the water volume in your bathtub, for instance, will be an infinite homogeneous media. Okay,
okay, and
because if
homogeneous,
you
it means
because if
this.
you move far away, the potential is so small, then the far away guys do not contribute. Okay, so it
Okay,
decays fast. It decays to
and what is
square, right?
homogeneity? It's the same
Homogeneity.
term.
Yes, good question. Yes, homogeneity in terms of this guy, in terms of conductivity. Yes, very good question.
So the
Yeah.
same conductivity, right?
Yes,
Over.
the same conductivity, exactly. Yeah,
Okay.
sorry. Yeah, the same conductivity, same magnetic permeability, okay? But this is the property of the material, okay? So,
Okay, now it's clear. Thank you.
yeah, okay. Then okay, now, uh,
Sorry, I think that I have like super stupid questions, but I look at the formula and I didn't quite get, because I see that there is something like r prime, and I didn't get how can we take the derivative from the like x y coordinates. It should be 0 or
no, let me explain you,
I'm
okay?
sorry.
No, no, that's very good. That's very good. Okay, see, each point in the plane or in the or in the 3D space, right, is encoded by a radius vector, right? By radius vector that has coordinates x, y, and z of the tip of this vector, okay? Therefore, we say that this point has coordinates r, okay? It's simply a vector where you subtract the x, y, z minus 0, 0, 0, right? So basically it will be x, y, z, which is your vector, okay? This guy located at location r prime. It's also radius vector. It can be, for instance, it can be 1, 1, 1, and this one can be like 0 0.8, 0 0.7, 0 0.8, for instance, right? So this is just simply x, y, and z coordinates, right? Uh, and then in this space, you have a difference between these 2 points, the distance between these 2 points, and you have the direction of the between from point R prime to point R. Okay, you can think of them as points. Just pick point A, point B, point C, but we just tell them that they are vectors. Okay, the directions are these points are described by radio vectors, right? This is that something. Is this a question or not?
Okay, I thought that
Sorry.
I thought that we should take the derivative on some
No,
step.
no. Sorry. Yeah.
Oh,
You meant
I'm sorry.
yeah, you meant prime as a derivative. No. It's just another location. It's just or R1. You can think of this
Oh,
R1. It can be R1.
okay,
Yes, it's just 2
okay.
points. Yeah. This point is R. This point is R. This point is R prime. Okay. We just take the difference because this is a radius vector that's pointing from R prime to R. That's all. Yeah. No, this is not a derivative. No. Thank goodness. No, it's just no. Much simpler. Okay. So yeah, basically, again, what it tells you, nothing more than the field decays as a square of the distance of the source till the point where you are measuring the field, and that and encodes the direction of the field, right? It encodes the direction that it points in the perpendicular to the plane formed by vector J, by the direction where current is floating, and this difference vector. Okay, that's all. That is all. Nothing else. Okay. And of course, the integration is just simply use sum. Okay, but then you go to homogeneous media, and since reduces only to the volume where the primary currents are floating, and you forget about the secondary currents. So you can basically say that if your neuronal source is located, in some gyrus and corresponds to some specific dendrites, you know where they are. You can tell that this is my primary current location, and I don't care about the rest. Okay, if you were to put the electrodes or your magnetic sensors inside the head, right, which you may inside the brain, right, inside the, let's say, in the place where the conductivity and magnetic permeability more or less the same. Okay, so but we are measuring things remotely, and they are things are a little bit more complicated. Okay, but before we do this, let's try to formally introduce the notion of current dipole. Okay, so first of all, we have to here we use, so we have this integral equation nevertheless, right? It's still, we reduce the volume of integration, but it's still an integration, it's still a summation of all primary currents that are floating in this volume, in the small volume. Okay, and the Dirac delta function, you probably had this in your preparatory class. Dirac delta function is a function that you can, well, you can think of this, well, it's a function that is equal to infinity at, in this case, at x0 and 0 everywhere else. Okay, so in order to understand what it is, it's basically it's a limit of this kind of thing, right, which is your rectangular function, where the area of the rectangle remains the same and it's always equal to 1. Okay, but the width of this rectangle decreases, and so the limit of something you get when you stream the width to 0, you have height goes to infinity, but because the width is equal to close to 0 and the height is close to infinity, the integral, the area is still 1. Okay, that's your shifting property of your delta function. Shifting is like, the theta. Okay, so, and the shifting property of the delta function is this: if you take the integration of any function with delta function in the volume, in the space, or along a single line, for example, doesn't matter, which includes point x0, then you get the value of function f at x0. This is, in fact, a strict way of introducing the value of a function, of a continuous function, at a particular point. Okay, it's only in the school you say that it's f of x0. Now, well, you can't do it in the high flow maths. You can't do that because nothing will work. Okay, in order to compute the value of the function at the given point, you have to take this integral. You have to measure the value of the function. Okay, and this is the process of measurement. Okay, like it or not. All right. So when you're working with some differential equations with something which describes continuous phenomena, right, which are changing smoothly in space and time, whatever. In order to introduce something discrete there, like you assume that you put a dipole, okay, so this is my, in this point, in this very narrow, very infinitely small point, there is my dipole, okay. You introduce it through a delta function, okay. You say that it's a delta function multiplied by whatever you want, okay. This will be current dipole, right? Now see, so your current dipole here, now this volume, see, the volume has changed there by current dipole, which is denoted by arrow, and it pertains to some very little, small, well, tiny point in space, and it has some direction, okay? But it's located in a, it's a little bit contradictory, but please kind of get used to it, okay? So, but it has certain direction. It's very small, and it's located in a particular point with coordinates RQ, okay? So used to be, it has to be RQ here, not R prime now, but RQ, right? So anyway, it's located at the point RQ. And you know that your current source now, your primary current, is not in this volume, but this is just in this very well-defined single point with coordinates RQ, R sub Q, okay? And then and then you, in order to do this, you have to say that it's Q is the strength of your dipole, multiplied by the delta R minus RQ, which makes this dipole exist at the point RQ, okay, in space. And this EQ is orientation of your dipole, basically where the current is flowed, okay? And then you take this guy and you substitute it in here. And this is integration over the volume, which includes point RQ. And then you simply get, for B, you get the value of the function which is under the integral, okay, which is under this guy, and then you have to scale it, of course, by Q and E. This is part of this, right? And then you get, now your Q is Q vector is Q times E sub Q, right? Which now Q is your vector, this red one, right? And for the magnetic field, you just have to multiply, to take the cross product of this vector Q, the current dipole, with this R minus RQ, R minus RQ cube, okay? And this is just a scalar, you know, this is just the length of the length between this point and this point raised to the third power, okay? Because this tells you the absolute value of the vector, right? The length of the difference vector. And this one is the vector that has direction, that encodes the direction towards the points where you measure in the field and the distance, okay? But the distance here is nominal. I mean, you can basically, you can put normalized distance here. You can put R minus RQ divided by the norm of R minus IQ, but then you have divided by the square of the distance already, right? Because and the square of the distance basically is the speed, is the how to say, is how rapidly the field is decaying. But this is property, this is quadratic dependence. Magnetic, like gravitational field, also decays as R squared, okay? And the brightness from something, from a source, also decays as R squared. This is a universal rule. That's all. So basically, now we have, in the homogeneous media, we have arrived from a very general set of equations. We have arrived at a very particular equation, which is basically from your school years, right? Tells you how to compute the magnetic field due to a current dipole, piece of wire where the current is floating, okay, at location RQ, I'm sorry, located at RQ, and the magnetic field and electric potential as well, very similar formula, but at location R, right? So basically, see the electric potential, this is what we would use for the electroencephalography. It's the same expression, almost the same expression, with just different scaling. Of course, depends on the conductivity, right? And if the conductivity is zero, then you will have a well, sorry, if the conductivity is infinite, then clearly you will have zero potential, because there will be no difference between the 2 points, because the conductivity is infinite and all the charges like exchanged already between these 2 points, right? There is just, you know, and if the conductivity is zero, then you will have an infinite potential, right? Because because there have to be infinite work that has to be done. It's impossible to do the work over the over this distance, because there is just simply no conductive media between the 2 points, right? So that's the intuition, right? And the difference here is, again, here you have scalar product between the 2 vectors, and the potential is, remember, the scalar function, right? And it also tells you how the potential depends on the orientation, how the orientation of Q and orientation of the vectors that is pointing to the location where you are looking, where you're finding this potential, right? So it encodes with the scalar product. It's a cosine between these two, right? So it means that the potential will be strongest here, of course, because the current is floating in this direction. It's changing the potential here, slightly here, less here, less here, less here, and doesn't change any potential at this point, which is perpendicular, which is in the perpendicular direction to the current flow, right? And in the magnetic field, slightly different, but the perpendicular, the thing is also there, because basically you have a magnetic field lines that are shown by circles here, and the field is pointing like tangentially to these field lines, right? And if you are right, if this angle is 90 degrees, then you have the large, because it's sine of this angle, right? This cross product, it expands the modulus of this multiplied by the sine between these 2 vectors. If it's perpendicular, then the field is strongest, but the further away you move from it, with the angle increases, the smaller the magnetic field will be. Okay. Again, this is a finite source. It's very short. Okay. If of course you have infinite wire, then the field will be the same, uh, given that this distance is the same, right? So the field will be the same along the whole line. But this is only a very short interval in space where the current is floating, and the largest magnetic field will be here, smaller here, smaller here, smaller here, and zero here. Okay. So that's, but this isn't homogeneous media. Okay. Again, this is just this very similar, just told you.
Wait, can we come back to?
Yes. Yeah.
So the silly question about notation, can you repeat again what is BR, what is VR, and what is JR and Q?
Okay. Yeah. BR is your magnetic field. It's a vector of magnetic field at location R. Okay, just, is it okay?
Yeah, it's strength
Okay.
of magnetic field, right?
It's a strength of magnetic field. Yes, yes, it's a strength of magnetic field. Yes, yes, it's a strength. It's the absolute value of this vector, the length of this vector is the strength of the magnetic field. Okay, but the direction of the vector is basically the field line, basically, which shows you the direction where the force that is applied to the charge, for instance, by the will act. Okay, so field lines. Okay,
Yeah,
so
yeah,
when you define, for instance, when you define the field line, the field of speeds, of velocities of your car, of your, some of water floating, right? Then you say, okay, the length of this vector is equal to the actual speed, okay, to the amount of like meters per second, right? This elementary volume is moving, right? And the direction is equal to the direction where this volume is moving, right?
Yep.
Yes, here you say that, okay, the length of the vector is equal to the strength of the magnetic field, напряженность магнитного поля in Russian, okay? And then the direction in which it's pointing is equal to the direction in which, let's say, if you take a unit charge and how it will act, how the field will act on this unit charge, you can, which it will be moving, okay?
Okay, but now about VR and J.
Yes, VR, yes, hold on, everything will be there, yeah. Okay, J, again, J is your current JQ primary. This is the so-called current density at location R. Okay, it's how much of current you have an elementary volume at location R. Okay, and we approximated it with current dipole. Okay, we said that we have a very small piece of wire where our current is floating, and this wire has certain orientation. This orientation is EQ. Okay. Okay.
Yes.
And the strength of this, if you take the wire, the current multiplied by the length, this will be the strength of the current dipole. Okay. So it's Q. It's just scalar Q.
Okay.
But Q multiply, and EQ is unit vector. So Q multiplied by EQ gives you current dipole. Okay. Gives you a current dipole located at R. and nowhere else. Therefore, we use this delta function r minus rq to show that this whole thing is located at location rq. Sorry, yes, I said r. It's located at rq. At rq. But this one, you have to not confuse this. This is current density for any r. Okay, you have to understand that this one is a expression for any r, and because of this delta function, this guy is 0 everywhere except at location rq because of this. Because of this property of the delta function, okay?
Okay.
All right. So
And
now, and V, right? V, yeah, V. V, well, okay, if you are in conductive media, then as I mentioned, we spent like 30 minutes on this Laplace equation. Laplace equation is an equation about the potential. Okay, the potential of the electric field. The difference of the potentials is something that you call voltage, okay, in your everyday life, okay? And difference of the potentials between CZ, for instance, and some reference electrode is something that you measure in with electroencephalography, okay?
yeah,
And so this potential, by itself, potential is a function that is defined up to a constant. We just assume that potential for simplicity, for convenience, that the potential in the infinity, from the sources, right? It's 0, right? This is how we made it single valued function, right? So it's the infinity at 0, okay. And then the potential at location r is equal to this, which is it's a scalar. It's just a number, okay. And this scalar is proportional to the current strands, right? Because this is the dipole, right? This is a vector. This is red thing here. It's proportional to it's reciprocally proportional to the square, because the first order here and the third order here, overall square, reciprocally proportional to the square of the distance between the point where the dipole is and the point where I'm looking at this potential, okay, where I'm measuring it, okay, at point
okay,
R.
it's clear. And
Yeah,
now back to
yes,
the equations in the left top corner. So the
okay.
nabla of magnetic field and nabla like with cross product. So it's conditions of existence of magnetic field or what? What?
Okay, see, yes, okay, see, the top one here, it tells you that there are no, because it's divergence, right? It's a divergence of magnetic field, right? It's
Okay.
always 0. It tells you that there are no magnetic charges, okay? So there's no such thing like magnetic charges. You
Okay.
cannot have a magnetic, you
Yeah,
cannot,
yeah, right, right.
yeah, okay. Uh, the second one is very simple. It's simply, I always forget, it's Ampere's law or something, or Biot-Savart Ampere's law, whatever. So basically the idea is that the rotor of B, the intensity of vector B, the rotor is nothing. It just tells you that it's rotating. Okay, the field lines look like this.
Yeah.
Okay, it's just that's it. Okay, and this rotor is proportional to the strength of the current. That's it.
Yes, I see. Okay, thank you.
So, and if you're able to say that without this operator, if you just say that, okay, you know that B is always in the plane perpendicular to J, you can replace then this guy by these words. Okay. Okay.
Oh,
That's it.
right. Because by
Yeah.
cross product we're obtaining a perpendicular vector.
Perpendicular. Yeah. Well, by cross product, when we use it, we then find this, right? That basically now the current, because if this guy in the plane perpendicular to the plane in which B is rotating, right? Then if we are given this guy and we are given a location where we are measuring the field, we cannot this direction of current and this direction here define the plane, and the field will be in the plane perpendicular to the plane formed by these two vectors. Okay, this is what this equation is telling you. Okay.
Yes, yes. Thank you.
Okay, so it's just that's it. It's nothing. Just the both geometry and the differential thing. Okay, are in the same in a single equation. Okay, but here differential thing is only about space. Therefore, you don't even have the derivative with respect to time here. Okay. All right. So thank you very much. See, when you ask questions, I think other people understand even also better because you forced me to explain things which sometimes are difficult because I know these things. I kind of got used to them. Not that I understand them, but to some of them I got used to. So okay. Now, so that was a closed form solution, right? Basically, school year formula. for a electric potential and the magnetic field due to a source located at location RQ as measured at location R. Okay. So now what if we have a volume which is on the one hand doesn't have uniform conductivity, because we have brain, we have cerebrospinal fluid, we have skull, which is 20 times less conductive as compared to the rest of the, to the brain volume, right? And then you have the skin and stuff, right? So you have different conductivities. So the question is, now you have the source, the primary current inside the brain, and you are interested in the potential which occurs on this skin layer where you attach your electric electrodes, right? Your EEG electrodes, and you are interested in magnetic field that occurs in the vicinity of the brain volume, okay, of the head, in the vicinity of the head. Okay. All right. It's complicated, but I'm not gonna, spend too much explaining you this, but I'll just tell you this. This thing can be solved. It can be solved analytical, well, nearly analytically. It can be, you can say that, okay, you have this boundary, it's so-called boundary element method, where you define the boundaries of the same conductivity. Okay, so basically homogeneous boundaries of the homogeneous volumes, right? That's what we looked at before, right? So within these boundaries, you can apply that simple rule, okay, which is here, okay, within the boundary. But we are interested, our source is inside the innermost boundary, and our interest point is either on the outermost boundary or just next to it, right, in the outer space. Okay, so the solution for this is given by this equation. I'll just try to explain this to you, and that's it. I will not go into details, okay, because then I give you simplifications which are again there, okay, and which makes things much simpler. Okay, so the magnetic field outside this volume, somewhere here at location R, is equal to this magnetic field due to the assuming that the whole medium has the same conductivity equal to the innermost volume conductivity. Okay, this is B0 of R, so the main term is still this. Okay, so you basically assume that there's no head. Okay, like we transitioned from like here, you assume that it's here. First you assume you are like this, right? You are in fact in this situation, but you first assume you are here. Okay, and you compute that B0. This is B0. Okay, this is B0. Okay, and then you have this correction term. Okay, I'll try to just give you very simple intuition. Okay, now this is just a summation that goes over each element on these boundaries. Okay, each element of the boundary between the media with different conductivities, right? And each element in this boundary is considered like a source. And this source itself is producing the magnetic field. And you just have to sum up all these magnetic fields. You can ask me, why on earth you have sources at the border of conductivities? Well, it's very simple. You have different conductivities. You have certain value of potential here. The conductivity here is one value. The conductivity here is another value. Where there is more conductive, the currents, the particles will want to float from less conductive media, which are right on the border, right here, from less conductive media into the more conductive media, right? Because it's simpler to move there, and the particles will want to move in there, right? The intensity at which they move depends on the difference of conductivities, right? It's like if you have, heat equation, pretty much the same. If you have something which is heated, you bring it into the room, which is cold. The room is cold, for instance, negative temperature. Then the heat exchange will be more intense when the temperature difference is high, right? And the smaller the potential, the temperature difference, the smaller, the slower will be the heat exchange. That's not not a very correct example, actually. I just realized, but anyway, because its temperature is rather the potential than its conductivities. Okay, but still, okay. Now another thing. Remember from school. Remember Fresnel diffraction. If you have a light source, and this light source, light wave, light front, and you are hitting some narrow hole, which the current is float, which the light has to go through, then Fresnel suggested to describe this process by placing a lot of sources at this border. Okay, you can think for this is exactly the same thing. This is electromagnetic phenomenon. It's just conductivity here is something different. You can think of this as you have completely transparent media here, and in this location you have completely non-transparent media. The conductivity changes, right? And here you can think of this as semi-transparent media. Imagine some made piece of glass, okay, which is you can't see through it, but not quite, and then you basically your light which will make through this hole can be described by the summation of light that makes through a little element of this hole, right? And each little element is a light source. The same here. Our current is floating. It's hitting the boundary between very well conducting media, which is inside the, let's say, inside the skull, right? And the skull itself, for instance. The skull is poorly conductive media. Most of the current will reflect from it, right? Will reflect from it based on same as optics law, right? Just simply reflect from it. But some of the current will get into this, and then it will be kind of sucked out into the scalp, because the scalp is the skin, and the skin is much better conducting thin than the scalp. Okay, sorry, the scalp is the skull than the bone, right? So the skin is more conductive than the bone, and therefore it will be the current that make it here kind of will get sucked out of there. But the same as you have a single source here, for instance, right? But you may even have think of this as like a point source, for like very narrow light, not the flat wave, flat wave, but like on the contrary, very narrow. It hits something non-transparent, and it starts propagating, starts smearing, right? It starts spreading and then producing something very diffuse on this end. Very similar thing here. The current floats here, hits the boundary, diffuses. Some of this gets sucked out, because the conductivity here is much better than inside. Okay, as soon as it makes it here, just really the potential will suck it out. Okay, and so that means that every point on this border is an elementary source. The strength of the source is equal to the difference of conductivities between these two media, right? And that's basically it. The strength of the source is difference conductivities and the potential at this point, because this is the current, right? Conductivity, difference of
So
conductivity.
can I
Yes,
ask
go
a
ahead.
question?
Yes, sure, go ahead. Yes.
Every point on which border? On the border of the skull or on the border of the source?
Which point? Sorry.
Like
Every point on each surface. On each surface.
on the
So
skull surface and on the scalp surface?
okay, we have electrodes which are located on the scalp. Electrode.
Yes.
Where we are measuring things, okay? But this equation tells you to go over all n borders. Okay, in this case there are 3 borders. 1,
Yes.
2, and
Yes.
3.
Okay.
And
Okay.
so
That
yeah,
was my question.
yeah. So you have like
Yes.
every current, the same. Think about like light source. Light source. This is not very transparent. This is transparent. This is not very transparent, and this one is transparent. Okay. So the light goes here, and this is the direction of your light. Okay. The light goes here, gets spread out on some angle here, right? Because it's not conductive, it will float away from it, but some of this will go through. And then goes further through this, but the law is exactly the same. So basically, it's all these currents, they will create the potential difference, and this potential difference multiplied by the difference of conductivities will be will make the current source, basically elementary current source that you need to sum up. So basically it tells you that, because you can always, of course, you can take this integration, you can put this integration over here, right? Because it's all linear. So, and you're basically summing up over all over the all, like in this case, three surfaces, three boundaries, and each boundary you integrate, you take each source, each elementary source, and compute the magnetic field of it. Okay, because this guy multiplied by this is equivalent to this Q, but it's very small elementary Q, elementary current dipole. Okay, that's it. And that's the only thing that this formula tells you. And about the potential, very similar equation. Again, you know, the currents, but of course now you're talking about the electric potential, not about the magnetic field. So you don't have cross products, but you rather have scalar products, because every current source produces the potential, the potential right here, right here. And the current source, elementary current source is your Q, and this is the scalar product, right? And it has also some directional preferences. So there will be more potential directly along, you know, in the direction where the current is floating. This is clear, right? And that's why you have scalar product, which means that the absolute value will be absolute value of this, absolute value of this, multiplied by the cosine of the angle between these two. If the cosine is, if the angle is 0, then cosine is 1, right? So you get the largest change in this direction, smaller change here, smaller here, here, here. But here you have to do this for every elementary source. Okay, all right. So, and this is, I put the glass here. This is the phenomenon. Basically, this is what you see when you visually the change of conductivities. You can think of this as the change of optic properties of the media. Okay. So, all right. So,
Can we take a break?
already? Okay. Yes. Sure. I will work on the laptop, on the tab to connect. 10 minutes. Is it okay?
Sure.
Okay, so we'll start at 6:10. Okay, resume.
Okay.
Yeah.
Maybe you can stop recording, or you already took off your headphones. I don't know.